Good afternoon, folks. How are you today? We are in week 3 of our classes. We spent 2 weeks learning how to solve one equation in one unknown. Essentially, we learned a number of methods to find root of this function f of x. Along the way, you learned about correct decimal digits and significant digits and how we can assure that our root has certain specified number of correct decimal digits or significant digits. So among the methods we learned, we found out that Newton-Raphson method was the fastest method, but it requires the first derivative of the function. So if first derivative of the function is available, we want to use Newton-Raphson method, which we know is same as fixed iteration method if we choose that function g of x whose fixed point we want to find as x minus f over f prime. Now I want you to remember that we can write this function, this equation, in many different ways. So we can express this function in many different forms so that it will have the same root. And some forms of functions are better than other depending on their first and second derivative. So you should remember that. Now, I derived Newton-Raphson method geometrically. It is also derivable from Taylor series. Taylor series is something you must have learned in your calculus courses. We are going to talk more about Taylor series. So if you didn't learn it in your calculus courses, I am hoping that you will learn it in my course. But let's see what Taylor series says. So Taylor series says that if we have a function and we know a lot about the function at x. What do we mean by we know a lot about function at x? Let's say we know the function value and its derivatives, how many ever that we know. Then at some distance h away, and h can be positive or negative, doesn't matter. Taylor series allows us to predict what the function value at x plus h is going to be. So the Taylor series says f at x plus h would be f at x plus h times first derivative plus h squared by 2 factorial times second derivative and so on. So we'll talk more about it. Let's consider, for instance, thinking about truncating the Taylor series after the first two terms. So we are going to neglect these higher order terms. So what happens in Newton-Raphson method is we want to find out h and think of h as same as delta x. We want to find out delta x that first time when we made a guess x. Next time when we want to make a new guess, our new guess would be f at x plus delta x to be 0. So we want f at x plus delta x to be 0. That's what we want. So if we look at Taylor series, therefore, Taylor series says 0 is f at x plus delta x times f prime x. So delta x therefore becomes minus f over f prime at x. So this is what we found about Newton-Raphson method. So you can see it is easily derivable without looking just at geometry, but we can derive it from Taylor series. So you saw that when we implemented Newton's method, it was extremely simple, really very easy. For your problem, it converged in something like 4 iterations. In my problem, remember I was trying to find square root of 5. It converged in about 4 iterations. And I told you that this method is used in implementing the square root key on your calculator. So when you try to find square root of any number, it uses this method. So I described to you as that your square root key is something like finding fixed iteration point of a function g of x. And I said Newton-Raphson method is same as fixed iteration method if we choose g of x to be x minus f of x over f prime x. So remember, this is the delta x of Newton-Raphson method. And this is the x nu. So we are doing the same thing as Newton-Raphson method. So we know our function is x squared minus a. So if you take its derivative, we'll get 2x. So our iterator g of x becomes x minus x squared minus a over 2x. We simplify it, 2x squared minus x squared minus a over 2x. So we will get x squared plus a over 2x. So it turns out that this always converges to the positive root. So we got lucky. We just happened to choose a form that was mathematically turns out to be pretty good. So let's see how this works in your calculator. So here is my square root example. Let's say our method input, we want to input our value whose square root we want to find. We'll call it a. And as I told you in my last lecture, Excel can compute up to 15 significant digits. You should find out how many digits does your calculator display. I bet you it is less than 15 digits. But let's say we wanted to implement the square root key in Excel. How many iterations it would take? So Excel has a limit of 15 digits, 15 significant digits, 15 to 16. Let's just use 15. So this is going to be our relative criteria. So we'll call it error. Okay. So we have two names, A and error. So let's start programming our spreadsheet. Our first guess is it going to be equal to A. We are going to compute the function. Remember, ideally I would have made it as a VBA module function. But since our function is so simple, let's just type it. So we'll type x square plus a divided by 2 times x. And one way to write 2 times x is to divide by 2 and then divide the result by x. So our delta x is x new minus x, and relative criteria delta x divided by x new, we want to be less than equal to EREL, and we have not converged. So let's go ahead and increment the iteration counter, and our new guess is going to be g of x. So notice this was the initial values. We typed in formulas here equivalent to one row. So now we are going to copy these formulas down. And let's say I am going to say that any root value is going to be guaranteed to converge. This method, fixed iteration method, is guaranteed to converge in 10 iterations. So let's go to 10 iterations. So you can see it already converged in 6th iteration at this for this value. Let's suppose we use some bizarre value. I'm just trying. I've never tried it before. But here is my 6-digit number. Notice converged in 10th iteration. So what we can do is we can mathematically show that it would guarantee that we would converge to 15 digits in so many iterations. And that is how we will program our calculator key. So what we can do is we can design a application specific chip, an integrated circuit chip, IC chip, whereby given a function x squared plus a divided by 2x, what we do is we feed an a to this chip. This chip computes g of x, calculates this x new, this function value, which is fed back in, say 10 times. And out would come square root of a to 15 significant digits. So what you might like to do is think about how would you design a application specific chip to find, for instance, value of pi or e to the power 1 or sine of some number, theta, and so on and so forth. So this kind of method is used in your calculator function key. And of course, if the derivative is unavailable, then secant method is our best choice. Remember, our function need not be known analytically. It can be a black box because it is not stated explicitly. It is embedded in a hardware or software system. And also be aware that it may be expensive or time consuming to compute or determine function of x. As an example, imagine, for instance, I have a simulator. In this simulator, I feed in temperature. And since some of you may have taken material science, let's say this simulator simulates, say, some number of atoms. And it finds out at this temperature what is their equilibrium energy. So it finds me the equilibrium energy, which is function of temperature. And I may want to minimize this energy, maximize this energy, or make it go to zero. So you can see I'm trending towards a root finding method. Except that to compute this function of temperature may require a lot of effort. So a supercomputer may require maybe 2 hours of time. So I cannot repeatedly compute this function unnecessarily at the same temperature. So I want to basically conserve my calculation. So I want to make sure that I only compute the function at a given temperature only once. So that is why it is very important that you write your software, say your root finding software, which is very efficient, which minimizes function calculations. And you're going to see how we are going to do that in our next example. So be wary whenever you are function computations are expensive, maybe belong in another package, or it is a hardware, another software. Try not to use package uh, software packages such as MATLAB. Try to write your own program, maybe in VBA, maybe in C, even in Excel, because eventually you're going to call that function from a Visual Basic routine. All right, if you're not impressed so far, let's see. Can we solve one equation and two unknowns? So when we look at one equation and two unknowns, we have this function. Let's say our two unknowns are x and alpha. So what we do is we treat our second unknown, alpha, as a parameter, and we do a parametric study using a root finding method. So we'll vary parameter alpha and solve for x using a root finding method. So let's see an example. You may remember that in my first lecture, I talked about modeling and how we come across one equation, one unknown for even a simple problem. So let's imagine we have a cylindrical trough, a pipe lying on the ground, and it has a radius of r and a length of L. And this cylinder is filled with some amount of water. So we are interested in finding out what is the height of the water. So we start modeling it. We say, well, to find the volume of the water, we can find what is this area of the circle, part of the circle, and multiply it by length. This will give us volume of water. So it turns out, if you look up handbooks or you try to derive it yourself, you will find out that the volume of water is a function of R and H to find the area. So it is this whole equation that I'm not going to repeat on the paper times L. And then if you look at the volume of the cylinder, it'll be pi r square, that's the entire area, times L. So if we take a ratio of the two, we divide this by pi r square, we will get this equation. You can see length goes away, so length is a material, and we'll get this big whole equation. We can normalize this equation by this radius r. And then if we define x as this ratio h over r, we can eventually even eliminate the radius. So we will get alpha is equal to all this equation, and this equation you can see right hand side there is only h over r, which is equal to x. So if we take pi to this side, we'll get pi times alpha, and we subtract pi alpha from both sides. So we'll have our equation f of x is cosine inverse 1 minus x minus 1 minus x square root of 1 minus 1 minus x square minus pi alpha is 0. So you can see that what we have here is we have an equation of the form f of x, but it also has this parameter alpha. So what we can do is we can vary parameter alpha and find our solution x. And we know our alpha can go from 0 to 2. So our height when it is full is 2r. So let's see how we will implement this in Excel. Okay, so I have set up already a template. But before we go on to the template, let's look at our Visual Basic macro. So in our Visual Basic macro, what I have here is I have a function f of x and alpha. So notice there are two inputs. Just to keep things simple, what I'm going to do is I need to compute this cosine inverse of 1 minus x. So I'm going to compute it first. It turns out that VBA does not have a cosine inverse function. It does not have a sine inverse function. The only thing it has is a tangent inverse function. Of course, we can express cosine inverse in terms of tan inverse. But let's suppose we don't want to do so. We know that there is a cosine inverse in Excel. So what we do, and that function is called a cos. So we'll find cosine inverse 1 minus x in Excel. So we will prefix it with this word application. Application refers to Excel. So we are saying go to Excel, compute cosine inverse of 1 minus x, and let's call this value COSINV. Same way, we want to get a precise value of pi. So we know Excel has a function called pi. We import that function and call that value PIE. So now we can program in our function f is cosine inverse minus 1 minus x times square root. So notice in Excel the square root function is sqrt, but in Visual Basic the function is sqr. So we have this function minus pi times alpha. And then we have this secant function. So notice, remember, we were going to be computing the f1 and f2. So as I said, if it is expensive to compute, don't keep recomputing. So don't compute inside the function as well if you are going to compute it for your Excel table. So here I have dx secant, which we know is a function of these four things. So I have programmed that. Okay, so let's start programming. This is our first guess, x1, x2, and let's say we want 4 correct decimal digits. So we have our absolute criteria EABS. So what we are going to do is we are going to say, let's say we start alpha goes from 0 to 2. We know the answer at 0. We know the answer at 2. So let's start with steps of 0.05. So alpha is 0.05. And we are going to say, let's remove this for the time, that this is equal to x1. Then we are going to say this is equal to, let's delete this, equal to x2. Then we are going to compute function at x1 comma alpha. We are going to compute function at x2 comma alpha. And then we are going to compute the function only if f1 is not equal to f2. Remember, this is what you did in lab number 2. If f1 is not equal to f2, to avoid division by 0, we'll use the function dx. We'll pass all these values, x1, x2, f1, f2, 4 values. But if f1 is equal to f2, then we will say delta x is 0. And then, of course, our x new is x2 minus delta x is x new. And then we are just checking our absolute criteria, whether delta x is less than EABS or not. So now what happens is, what I want is, I want this x2 to go to x1 here, and I want x new to become x2. So previously what we did was we made a table. So I would have expanded this and I would have made a table, and eventually we would have converged. But now what I want to do is I want to solve this problem all in one line. In order for me to do that, what I want to do is I want to say at some beginning of iteration, this x1 is x1 here, this x2 is x2 here, but after that this should come here and x new should come here. So I'm going to set up a flag and I'm going to give this flag a name, iterate. And initially this flag's value would be false. So when we are beginning to iterate, its value is false. So the way we are going to program it, we are going to say if iterate is equal to false, then use x1 as an initial guess. Otherwise, use the value from here. Okay, same thing here. If iterate is false, use x2 as initial guess. Otherwise, take the value in this box. I must go. Made a mistake. Typing mistake. Okay. Now I want to begin iterating, so I change this to true. And it gives me this error message. Of course, I have circular references. It says there are one or more circular references because now my x2 formula is in terms of x1, my x new is in terms of x2 and x1, and then finally I have a roundabout formula. So I say, yeah, I know about that. So let's try to fix it. So the way we try to fix it, we say we are going to do manual calculations. And here is how we go about doing it. So we go down our file menu, go in options, go in formulas, and we say right now By default, usually it is in automatic calculation mode. So we are going to put it in manual mode. We don't want anything to be recalculated when we save the worksheet. We want to enable iterative calculation, and we want to do one iteration at a time. And we want to ignore this maximum change option. So we'll set this to some very low value. You know our limit is minus 308, so I could have set it to minus 308. So the key thing is when we are in manual mode, it is not going to keep the workbook in automatic calculation mode. So I'm going to, so we change this to true and press F9 key. So we have already done one iteration. We do another iteration. And you see now 0.1 has come here, 0.23 came here, and we have a new value 0.19. We do once more F9, third iteration, and then fourth iteration, fifth, and on fifth iteration, it converges. So now we know that this is our solution when alpha is 0.05. So this is great. So let's go back to begin iteration. So I'm going to press F9 and we reset it. So now what we want to do is we want to do a parametric study. So we are going to increment this by 0.05. We need to get some new initial guesses. So what we are going to do is for x1 we are going to use x2 of the previous row, and for x2 we are going to use x new of the previous row. So we are going to say if iterate is equal to false, get the initial guess from here. Otherwise, pick up the x2 value from the same row. Same thing here. We're going to say if iterate is equal to false, use this as our initial guess. Otherwise, use x new from the same row. And that's it. All we need to do is copy all these formulas down. So we are going to increment this up to about 1.95. No, let's see. We want alpha can only go up to, let's see, 95%, right? We know the answer when it is 100%. I'm in manual calculation mode, so that's why it was not calculating. So let's go some more. Okay, here we go. So we are up to 0.95. So what I'm going to do is I'm going to slightly reduce the magnification so you can see all of them. Okay. So we have set up our spreadsheet. Let me press F9 just to be certain. So these are my initial values. Note how they are chained up. Initial guess 0.05 coming here, 0.1 coming here, then 0.1 comes here, x new comes to the next row. So we do all this chaining. So we start iterating, set our flag to true. Of course, it does nothing because it is in manual calculation mode. So we press F9, second iteration. Notice one value has already converged. Third iteration, a lot of values have converged. Fourth, fifth, and in fifth iteration, our first row has converged. So apparently these were not very great guesses when alpha is 0.05. So we should have chosen an initial guess maybe near 0.2 or so. But in any case, we have solved the problem. So what we can do is we can plot alpha versus x nu. And we can see what that looks like. So we insert xy scatter, and you can see, so this is percent fill of water. So as we start going from bottom up, the curve is concave down as we expect because the cylinder is getting wider, and then it is concave up because the cylinder is getting less wide as the water fills up the tank. So the height increases more rapidly. Okay, so we have solved our parametric problem. Before we move to our next topic, which is error propagation, remember that whenever you are going to be reporting now a value, so you're going to say x approximate is something plus minus something. So when you report this, you're going to report how many ever significant digits that you guarantee. So for the plus minus, so if this is your x and this is your delta x, that would mean that this digit needs to be always rounded up. That's what we did in lab 2. So we always round this up. This digit, however, this is significant digit since we are using a rounding machine. This is what we are going to assume for throughout the course, rounding machine. So this one you should either round up or down looking at the following digit. So this always you round up, this you round up or down depending on whether this digit is 5 or more. So that is going to be our rule. So throughout the course, whenever you are going to be expressing an approximation, you must supply a plus minus figure. Often what people do when they are reporting in technical reports or research papers, whenever they list any number of digits, it is assumed that the last digit is least significant, but significant nevertheless. That it can change by 0 or 1 units.